Detail. Anyway, thank you very much for having me here, Daryl. And again, I had a slight change of talk. I am going to focus on landmark manifold and not general Lie groups and orbit spaces. This is, of course, joint work with Stefan and Alexis and Helene. And I think Stefan and Alexis are going to cover much more general follow-on talks. So I think this is almost, you can say, part one of 3 talks that are going to happen. And Stefan is going to talk on Thursday and Alexis on Thursday, right? Yeah. So, okay. But in general, I'll basically set up the problem and show. So, we've heard a lot of work talk about geometry so far and looking at doing kind of analysis of objects that live on manifolds, and kind of problems I'm interested in is really looking at on brain shape and shape of anatomical changes in computational anatomy, in which the data either comes in as images or you somehow or other get kind of landmark points that allow you to describe a shape. And what I'm interested in today is trying to do statistical analysis and trying to understand how do we look at collection of images and collection of data, not just a single object and a single image. So let's start with something very simple that a lot of you will be familiar with, and I will not make this statement all. In which your data, just say, lives in RD. So you have finite dimensional, nice simple points in a finite dimensional vector space. Then our standard kind of model, one of the simplest models we can use, is that the data is drawn from a IID Gaussian distribution with some mean, unknown mean mu, and some unknown covariance sigma. And this is almost like the first problem in statistical inference you learn, how to estimate mu and sigma. And one simple way of doing that is to do maximum likelihood, and you say you want to maximize this likelihood function with respect to mu and sigma, and that kind of captures the centrality of your data and how the data is spread out in terms of kind of that's captured in the covariance matrix. And that's a symmetric positive definite matrix, and everyone kind of is very familiar with this. And now the question comes is, how does this generalize this to manifold? What happens if your data lives on manifolds, and how can we do this kind of estimation? So I think one of the earlier models has been since you're on a Riemannian manifold and we're given some metric g, and I'm going to assume that the metric g is actually parameterized by some finite number of parameters. So we're going to with some theta. And then the first kind of simple model is you say that your data is modeled as being independent, identically distributed, in which your data samples are drawn from some kind of a probability distribution, and you kind of naively replace your exponent of the exponential with 1/2, but now the Riemannian distance from your data points to the mean parameterized by mu. And now the distance, of course, depends on the Riemannian metric, and you have this Persky normalization factor, which in general terms can depend on your mean mu as well as the metric g. And this is the partition function, or the normalizing constant, is usually intractable and very hard to compute, and rarely can you have any kind of closed form solution for that in terms of your metric that's parameterizing the Riemannian distance between your data points and the mean. So I'm not aware of any previous work of trying to estimate g of theta directly in this kind of framework. Most of the time this has been used to kind of ignore the g of theta dependence and kind of use, and theta is the parameters of your metric. For example, in your case, your Eben metric had a whole bunch of parameters you could put in, the power, so the coefficients. So I want to make it finite dimensional parameters. So it's a parametric kind of family of metrics that you've got on your model manifold. So I assume fixed, and there's a lot of work in estimating the mean. You know, Xavier Pennock, Fletcher, Srivastava, Ian Dryden, and others have used this kind of a model to do the estimation. But there's another model to generalize the notion of Gaussian on a manifold, and that comes from the heat kernel. So the Gaussian distribution is also the fundamental solution of your diffusion equation, in which you have this is the Laplace-Beltrami operator, and the Laplace-Beltrami operator in local coordinates is given explicitly here, in which you have the gradient of divergence, and that allows you to define this diffusion equation and talk about its fundamental solution on the manifold. Now it turns out in RD, if we have the translation invariant metric defined by your covariance inverse, the two definitions are identical. You can either directly write down the probability distribution, and this happens to be also the fundamental solution of the Laplace-Beltrami operator, and you've got a really nice unified story. It doesn't matter which way you want to think about your data coming from, and you have got a closed solution. It doesn't matter whether you worry about. So a lot of this kind of differential geometry of the Rn. But of course, on a manifold, yeah, and so then the data now, what you're going to say is the data is identically distributed from the diffusion kernel at time point 1, and you're going to start with initial condition centered of each of the at your mean. So you're going to assume the data comes after you've diffused for one time, starting at the mean location. So that's the general model. And in Rn, these constructions are identical, but for a general manifold, these two constructions are very different. I mean, if you look at just the standard sphere, we know we can write down the kernel, not explicitly, but implicitly in terms of the spherical harmonics, with e to the minus eigenvalues of the Laplace-Beltrami on the sphere, and that looks very different than e to the simply distance squared on the sphere. And it is now the problem with this model is that this is not easy to solve for general manifolds. I mean, like I said, even for the sphere, it's given as an infinite series of spherical harmonics, and so in a sense, I'm going to talk about this kind of model of the data, and rather than the simple z times e to power distance squared. Problem comes is that this is not easy to compute, a Laplace-Beltrami operator on a non-compact manifold with arbitrary kind of parameterized metrics, and we want, yeah, there.
Does this mean that asymptotic solution is going to be a constant on the manifold?
Yes, the limit distribution for the heat kernel. Yes, but that's why I want to only diffuse until time point 1. So my transition density is, I'm going to define my density at time point 1. So that's important. Otherwise, you get kind of the trivial on a compact manifold, and on non-compact, it just goes to 0. Okay, so this is not easy to solve, but what I'm going to show today is that you can do efficient stochastic approximations of this quantity by using Brownian bridges. So that's the basic idea in which we're going to develop and then do inference using the stochastic approximation to the probability distribution that I've defined this implicitly. So yeah, and please interrupt me anytime so that I clarify this thing. Now where does Brownian bridges come in is if you look at a standard Ito diffusion on Rn, which is given as a stochastic defined by a stochastic differential equation with a drift b and diffusion coefficient sigma that depends on your position where you are as you're evolving. For Ito diffusion, the probability distribution of the random variable evolves in time according to the Fokker-Planck equation, and that's given by in terms of your drift and your diffusion process. Now, if this is constant, this thing again looks very much like the Laplacian, and a standard Brownian motion in Rn is exactly your drift being 0 and sigma being a constant square root of the covariance matrix. This is actually the definition that's used to generalize a notion of a Brownian motion on an arbitrary manifold M with a metric G, and it is defined as that Ito diffusion whose Fokker-Planck equation is given by exactly the Laplace-Beltrami operator on the manifold M, that whose probability distribution, transition probability distribution, evolves according to the Laplace-Beltrami operator. And since we have the Laplace-Beltrami operator in coordinates explicitly, one can rather straightforward show that in coordinates, if you have an Ito diffusion that's given by a drift that depends on the contraction of the Christopher symbols with respect to the inverse metric tensor and the square root of the co-metric, this diffusion process will have exactly its Fokker-Planck equation given by the Laplace-Beltrami operator. And here and you can see that immediately, because if you look at the drift term here and you write this in this form, you can directly see the connection. It's very easy to show that the Fokker-Planck equation of this diffusion is exactly the Laplace-Beltrami operator. So there's a link between stochastic processes, Brownian motion on a manifold, and your Laplace-Beltrami operator. But still now the question comes, how does one actually evaluate P? So, but before that I want to show you some movies and get a good feeling for what happens when you have, so let's consider the simplest Lie group SO3, but let's now put a right invariant metric that's not the identity, which is given by 0.5 to 0.5. And that's one of the things that I was really disappointed. You go and read any of the books on Brownian motion on manifolds and Lie groups, and the first thing they always do when you look at any nice compact Lie group is assume that you have a biinvariant metric, and that the metric is fixed to the identity, the biinvariant metric, which makes it really, in some sense, uninteresting, because we want to capture different variations. So we look at the hello. Why isn't this playing? Options. Trust this document always. Security. Yeah. So now here you're seeing the frame represented by SO3 going as evolving according to a Brownian motion. And the Brownian motion on Lie groups or manifolds, if you're given a metric, is really relatively easy to simulate, either in coordinates or just using the Riemannian exponential map. So you take little IID Gaussian random variables, project them by your metric, and exponentiate. And then you get little steps and you move it around. And here you're seeing the action of the SO3 acting on the base point and how it's traced on the sphere. And you notice you get a really nice elongated distribution. It's clearly not in any way symmetric a distribution of how the point is moving. It's definitely moving much faster in one of the directions where you have variance of 2.0. So is that clear to everybody? What I'm doing here on this sphere in SO3? Great. So now let's look at what's happening down on the sphere, the orbit space, because that will be very important when we do our landmark manifolds. So now this is a classic, I think this is a theorem from Martin and Darrow. That's where I found this really nicely stated. So if you have a Lie group with a right invariant metric defined by a sum in a product on its Lie algebra, and we consider the orbit of the group via its left action on some point, then we have a G0, the isotropy subgroup of X0, and we look at the left cosets and define the manifold of the left cosets of G via of the isotropy subgroup. Then the left G axis is transitive on this left coset, and you can define a metric on G via this minimizer. Then this metric, because of the right invariance and left action, this minimization defines a well-defined metric and is independent of choice of X0, and furthermore it's a nice Riemannian submersion. So you get a nice classic geometry of geodesics downstairs being lifting up to geodesics upstairs, and horizontal geodesics upstairs projecting downstairs, and you get a really nice geometric picture that links this metric that's defined here into a metric here. Now notice, this metric is no more an invariant metric because you lost the right invariance when you come down, like Peter likes to tell me. Going down, you lose one invariance in the generic case.
But you have to jump the same.
I have to jump, okay, yes. Yeah, I mean, I've been listening to his talk for last so many years, so now I'm able to use, repeat those words like a good parrot at least. I'll start to jump soon. So we have this nice picture, so we can use this to do our stochastic simulation, and this is where it's going to come in important in terms of the horizontal lift is also very well given, and I'll use this a little bit later on. So we have this, if we consider a curve, and we can define the curve on the manifold since it's transitive as having a curve on the group that's at the identity. And so if you want to look at little tangents mapping, you can look at the define a linear mapping from the Lie algebra to the tangent space at each point, where simply the derivative of such a curve, where this curve is actually a curve sitting at the identity on the group. And the kernel of this map is exactly the Lie algebra associated with the isotropy subgroup. And we can define a horizontal lift of the tangent vector from the manifold onto the Lie algebra via this minimization. So this is you defining the horizontal lift from a tangent vector x. So we want the projection of the element in the Lie algebra down to the tangent space of the manifold to be u. So we are trying to lift u horizontally up to the group. And this is very abstract setting, but we can do this explicitly. So, oh, by the way, these are questions that I've been trying to research for the last few weeks and have not actually found, and this seemed to be really straightforward, but it's really hard to find anything. So if anyone has any references for the sphere, it would be really nice. And one of the simple questions is, this is what we've done with SO3 acting on a point, let's say 1, 0, 0, and defining a whole sphere. And the simple questions come is, what is this now non-standard sphere? Because the metric I've induced on the sphere is not from the bioinvariant metric, it's from a right invariant metric on SO3. So I could write down, I wrote down the equations. It looks like cross product of x times u A, where the A is the inertial matrix associated with the SO3. But the question comes is, what does this non-standard sphere look like? Is it even embeddable isometrically in R3? Is it simply an ellipsoid? It kind of looks like an ellipsoidal metric, but the question is it really just an ellipsoid that we've got a very fancy description of with all the Lie groups and thing, or not? And what does the right invariant Brownian motion in SO3 project down to a Brownian motion on the non-standard sphere? And this, I think, I'm almost sure it's not, that the non-standard Brownian motion, because of the vertical horizontal, in the case of the if you use the bioinvariant metric, then actually Brownian motion on SO3 projects down to the Brownian motion on the sphere. But I think because of the fact that we lose this invariance, but I've not been able to find any literature on this setup. Yeah. Not sure, might be. But what about just the first question geometrically? Is it just an ellipsoid? Is this sphere, non-standard sphere, embeddable in R3 as just an ellipsoid isometrically.
The first question is it color-joint motion?
Okay.
After that, you'll have a calculable answer.
Yeah, I mean, the metric is easy to calculate.
Just compare the actions. If it's the same action as the co-adjoint action, then it should be the same. Right.
Yeah, I haven't done that. Maybe I can, but it's not obvious to anybody either that this is just an ellipsoid. No. Okay, good. And I've not been able to find any analysis of this kind of geometric picture of the simple SO3 on the sphere metric. But anyway, okay. So let's see. That was the first part. I kind of talked about stochastic process. Now, where does bridges come in? So you saw simulation was really easy to do, but simulation is not enough. We want to actually evaluate the probabilities of some data points that's given at time point 1 of the transition probability. So the basic idea here is not to just do is to do a guided diffusion. So you want to simulate an Ito diffusion which hits the data points with probability 1. And the idea is you want to use the expectation over the sample path to evaluate the transition probability at time point 1. So that's the basic idea. And once we have this evaluation, we can then simply take the gradient of this probability with respect to mu and the parameters of the metric to optimize. So that's the basic notion. And for that, we're going to look at what a Brownian bridge is. So a Brownian bridge is a conditional Brownian motion that's pinned at both ends. So at time point 0, it's 0, and at time point 1, it's also 0. And if you consider a modification of the standard Brownian motion, in which we add a drift term that depends on how far away you are from where the point you want to hit. It's simply given by I'm just talking about in Rn here, where you have x of t minus v, and you scale it by how far away you are from time point 1. You notice, because this thing, if x of t is not equal to v at time point 1, you kind of get this blow up in the drift. You notice that this Brownian motion will be exactly with probability 1 at v. So at time point 1, the probability that this Brownian motion is at v is exactly equal to 1. So this standard modification of the standard Brownian motion, so if you add just a deterministic drift term to a standard Brownian motion, you get a Brownian bridge that hits your data point, and that's great. Now for a generic SDE, the modification is given by a term that involves exactly the transition probability density. So if you want to take a generic SDE and say I want to make it into a Brownian bridge, you need to add a drift term which is given by the original drift plus the covariance times the gradient of the log likelihood. Yes, the drift will depend on t, and this is the transitional probability of going from time point t, you're at x at time point t, that you hit 1 at time point v. So in some sense this is even a lot more complicated than calculating the probability of starting at time point 0 at x and hitting time point your v at time point 1. In the interesting thing is, for the standard Brownian bridge, if you notice, this drift x of t minus v 1 minus t is exactly the derivative of e to the x minus t v squared divided by 1 minus t, which is the transition probability that you have exactly here. So because in the Rn we have a closed form solution for the transition probability density from any time point t to time point 1, we can differentiate it and get the modification, and it makes kind of intuitive sense. But that's the interesting thing is, but the whole problem was that's what I wanted, so this is intractable, so how am I going to build a bridge that has this probability transition density? And the great thing is to, but notice again, the important thing to notice is that the diffusion term is the same. Only thing that we need to modify is the deterministic drift. So this is going to be a very important property, and this is the key idea that Dillon and Hu exploited, and they said let's simulate a simpler Brownian motion, some kind of a Brownian bridge whose drift term is not the drift term associated with the true Brownian bridge of our SD that we want to simulate. So we do a kind of a greedy drift. Just use a drift from the standard Brownian motion, Brownian bridge. The cool thing is it has the same diffusion term as the diffusion term we want, but the drift term is not of this form. But the key insight is that these two processes, the y of t and the Brownian bridge that we did want to simulate, are absolutely continuous with respect to each other by Kirsanov's theorem, because they have the exact same diffusion term that's driving these two Brownian motions. So that's a very key property. So since they are absolutely continuous with respect to each other, we can actually use the simpler Brownian bridge to estimate exactly what this transition probability density is, and we can write that as probably your standard Gaussian probability distribution corrected by an expectation that only depends on the sample path of your modified process y, not on the original process that you're trying to estimate. So this is a really key insight. I mean, I thought this was, oh, and that's supposed to be pi, I forgot my backslash. So this is a really key insight. Because we have this, we can now actually get an estimate of p by simulating from process y, which we can simulate. That's perfectly well defined, because if we have the sum b of t and sigma of t with a greedy drift term, there's no problem there, and correct for the fact that our drift term doesn't match, and the difference in the drift term between our drift term and the one that we would have needed to do the Brownian bridge is exactly given by the gradient log p. So we can write down this correction term, and here it's given in terms of second variation, and it's pretty nasty formula, but this actually is really a limit of a rather simple intuitive explanation for the discretization of finite step kind of random walk that's the limit of. And here you can see it has two terms. One is a term in which you look at the how your covariance acts between your drift term and the original drift term, this inner product. And the other one, here you can really see the change in the covariance as you're going along the path, and this is going to be dependent on the metric. So we'll see this will really come into play, and this is really the key paper that we've used in the 2006 Dillon and Hu paper, in which they use this idea for, of course they were doing finance, so they were interested in stochastic financial models with a bunch of parameters in the diffusion process that they want to estimate, but it's the same basic concept, because now our diffusion process on in coordinates on a manifold is exactly had this form in which you had the drift term was given by the metric times the Christopher symbols, and this was exactly the square root of the cometric as the diffusion term that was parameterized. So our parameters were in the drift and the diffusion terms that we wanted to estimate from. So that's going to be the idea. So now I'm going to talk about in details the landmark manifold, my favorite manifold. So here the basic idea is, and you have already seen a lot of work on this, is the idea of generating a diffeomorphic transformations given some source points, starting here with a circle to some configuration given in red, and then you end up generating a diffeomorphism that matches these points, and we are exactly in this setup that I talked about, basically with SO3 acting on a point with a right invariant metric. So Here the Lie group is going to be a Lie group of diffeomorphisms with a reproducing kernel Hilbert space metric, and we had a really nice talk on how to do this in generically in PyTorch. So you can actually compute this really easily. And so this problem I want to use this framework setup is to actually, how do we estimate this right invariant metric on this diffeomorphism group that's parameterized? And the idea is the data comes from a diffeomorphic transformation downstairs of these landmark points, and you're given a whole bunch of these landmark points, and you want to estimate some parameters of the metric, and also the base configuration mu, which is the mean configuration of landmark points. So now we can directly apply our machinery. So we assuming we're given n set of distinct points in RD, and let diff RD you be the infinite dimensional Lie group of diffeomorphisms, compact support, so we are and let Q be the orbit of X, some initial configuration of n points under this by this diffeomorphism group. Then we are exactly in the same framework. Now Q is exactly has a dimension n times d, where n are the number of distinct landmark points, and if we have the isotropy subgroup of the n points, then the set of all diffeomorphisms that keep those points fixed, that's all the isotropy subgroups. And then we look at the definition of the large deformation diffeomorphic landmark manifold is exactly the homogeneous space, the left cosets of diff RD mod by this isotropy subgroup. So in that setting is exactly the notion of what we saw with the sphere and SO3 acting on it, except now our Lie group is of course not compact, it's the diffeomorphism group with a representing kernel Hilbert space and all that. I think that's the story that has really emerged over the last 10 years. And the great thing is we can directly write down the metric on the landmark manifold. And here the metric is, it's easy to write it in terms of the kernel metric, and I think you saw that already yesterday. And this is the given two tangent vectors. Those are nothing but little velocity fields at each of the landmark points. So this is an ND length vector. The metric is simply given by eta transpose KQ inverse, where KQ is the ND by ND covariance matrix defined via a kernel. And our standard kernel we're going to use for now is going to be a simple Gaussian kernel of the form alpha. Now here this is not the Gaussian distribution, but the actual just the Gaussian function defining the kernel metric between points xi and xj, and it's given by alpha and sigma. So the parameters of our metric I'm going to consider are simply the alpha, the height of the Gaussian, and the covariance matrix sigma. I'm going to assume it's completely translationally invariant and everything. So I'm going to parameterize sigma by sigma transpose, and we want to estimate alpha and this little sigma from our data. So now we are pretty much ready to set up the problem. So what we're going to do is we're going to, and this is going to be really convenient because we have a global chart. R&D is a nice global chart for this manifold, so we can write everything in coordinates, write our Brownian bridge in coordinates, do the diffusion coordinates, and do the estimation. So given a set of observations qi to qn, these are collection of landmark points, and it's distributed according to the transition density of a Brownian motion on this manifold at time point 1. Estimate alpha and sigma, and now we're going to perform maximum likelihood estimation by using the bridge process. So the algorithm becomes very straightforward. We sample j path, some constant, guided by our process y, parameterized by theta and qi that hit all our data points, given our initial some estimate mu. Then we actually evaluate exactly this expectation. This is the expectation over the sample paths that we have simulated. That gives us an approximation of the probability density associated with, and then we take just a gradient descent on the estimation of the log likelihood with respect to all our parameters here, in which case the parameters are the covariance matrix and our initial configuration of the landmark points. And the process, now I can write down exactly what the process we're going to simulate is going to be exactly the k, the metric is given by the inverse of the your kernel metric times the Christopher symbols. Now we're going to use this greedy kind of matching term that pushes us towards the landmark points, and then with a drift given by the square root of this kernel. So this is very explicit. Now the only thing, little complication, are the Christopher symbols, but Mario has computed them, but now we computed them in PyTorch, you know. What?
I mean, they are that complicated.
They're not that complicated. No, but now that we have PyTorch, why would you want to differentiate? You just write one line and it gives you the derivative, right? Yeah, and I think you also computed the Christopher symbols in your paper on Jacobi fields, if I remember.
I mean, Mario did it. I mean, when you compare the Christopher symbols to the curvature, that becomes a piece of cake.
Yes, compared to yes. But the cool thing is we don't need the curvature here explicitly, because you've got finite time difference. You know, you literally have to just take differences of the Christopher symbols at the different discrete time points. So that was really nice, because first I was afraid you'd have to calculate curvature, and Jacob did that too. And you know, we still don't know whether Jacob's calculation and Mario's calculations are identical. But
derivative comes from PyTorch and Theano as well.
yes, yeah, and PyTorch Theano also. Well, maybe not PyTorch, because curvature requires extra derivative. So I'm not sure PyTorch can give you that. But Theano does give you the curvature, and yeah, Stefan has computed all this multiple times in PyTorch and in thing. But anyway, so this is. And now here some of the, okay, so unfortunately I still don't have yet any nice brain images where we can show you some of the results, but here are the simple results of trying to estimate, showing how you can estimate the likelihood and the convergence of your parameters. So this actually works when we start with really like 5 times off on the parameters that you really converge, and here you can see the stochastic nature of your gradient descent. You know, maybe the step size is too high, and one can play with this. But the other thing I want to talk about is some open questions, and this is something that I think Phillips and I'll have pointed out: the long-term existence of Brownian motion, this landmark manifold. That's, you know, it's tough. This manifold is not compact. It's both positive and negatively curved and not bounded. So I'm not sure, you know, about this thing. My claim is, do we need long-term existence? You know, maybe we just need time point 1, and our data is the same. Okay, yeah. And the question really comes is, how do we do this in infinite dimensions? I mean, with landmarks, it was really nice. You had a nice finite dimensional description of the manifold, but what about curves, surfaces, and images, which is what we want to do? How does this, I mean, at some level the basic geometric construction holds, but the orbit spaces are infinite dimensional now, and then we have you know, I don't know how to apply this kind of estimation thing. And the question is, but since we still want our parameters of the RKHS are you know, finite number of parameters. If we use some kind of a metric that's parameterized, you know, like the ABC metric, and we want to estimate the ABC parameters or some kind of parameters there, you still have a small number of parameters, even though. So these are some of the open questions. One of the things, I'll end up with a nice horizontal lift of a Brownian motion going back up to diffeomorphism group. So this is now, the Brownian motion is still parameterized by finite dimensional distribution only at these points, and randomly simulate, we can generate random diffeomorphisms. And the cool thing you notice here, you see here, is that since the horizontal distribution is not integrable, you get really a lot of these compositions, and you get pretty huge space of diffeomorphisms you're spanning. So there's something there to think about. You know, do we need really can we get away with a finite dimensional diffusion, lifting up to the diffeomorphism, which is very a low dimensional section, and just estimate that, even though your data is given by curves and surfaces and images. So my sense is maybe we don't need to go up to the full Brownian motion on these high dimensional manifolds, or infinite dimensional manifolds. And there, I'll end and take any questions.
Thank you. Thank you very much.
So I'm back on track.
Thank you. So, questions?
Yes.
Okay, I have a bunch of questions, so I thought
Okay.
some of them probably will go offline. So the first one was related to the infinite time existence. This is a problem that we, I mean, this very situation is something that we worked with Valentina several years ago, and there were too many problems in what we were trying to do for us to go any further. So one of these problems was infinite time existence. So which ends up, it may be true I mean, I don't know if it's true or not in the landmark manifold. We were even able to prove it with three landmarks. But it's also because maybe we suck at proving this kind of thing.
Sorry, what?
With three landmarks, we were not able to prove long-term existence.
I think I can prove with one landmark.
Yeah, two also.
And two also.
The Hamiltonian along the trajectory and just differentiate it and look at the increase of the Hamiltonian and control it.
I don't know. I think we tried also something like that.
It's something we tried.
Because I mean, that would work with any manifold if you could do that. But it's not like there's always a Hamiltonian. Anyway, so we but maybe we did
the
it.
fact that it comes from the right environment.
Maybe we did it wrong. What happens if the solution do not exist in arbitrary time is that your Brownian motion is equal to infinity with positive probability at time 1. And so, on the other hand, if you look at the Brownian bridge,
Yeah.
you condition by endpoints, then
You can't go.
then that's well defined.
Right.
But do you know if your equations still hold for the density and all the picture of the Brownian bridge, even if the Brownian motion explodes with some probability in finite time?
I don't know. Technically, I think it would be a problem because you have to apply the Grisham theorem, and there is calculation of Grisham theorem on Lie groups. But you sent me that paper just couple of weeks ago, and I didn't get a really chance to. Were those Lie groups compact, or did it require compactness, or Stefan?
I think it's not that the Sarang theorem is not the main problem, but I think for Laurent's question, if it's growing up at some point at time 1, then so existence of it's not like the process doesn't even exist until time 1. So conditioning on hitting something at time 1 is.
Yeah, I mean all of those techniques.
Because we run on probability, so if you condition to not being to a non-explosive solution at time 1, then that's well defined.
But I think for this scheme to work, you need at least, I think, continuous density function at the time.
Yeah, so I think, I mean, you might be able to push it through. I don't think the exact current way the theorems are posted might not apply. But that doesn't mean that there's not a generalization of the basic framework. Because I think the idea of having, as long as, the big idea is as long as you have the two, so let's say if you can prove the bridge exists for both, then you know that the bridge exists with some other kind of greedy drift that's guaranteed to continue, still have the hitting probability. Then those are still going to be absolutely continuous with respect to the two Brownian bridges are going to be absolutely continuous. So if you can prove bridges existence, then you get the absolute continuousness of the two bridges, and then that way, then you could able to come to the this could still work. Does that make sense, Laurent?
Yeah.
Yeah. So that would, but I think
that you got the plan.
It's a plan. It's not. It's.
I had another question. If I
Yeah.
take that. So we also tried to play with the De Leon and Hu method. It was a different situation. We were not trying to estimate the metric, but we were trying to estimate the drift. But what we found was that it often happened when you have these exponential models and you're using a different proposal probability that we were rejecting changes. You know, you make a change, you propose, you accept with some probability based on the ratio.
What you are doing,
There's no acceptance rejection.
Oh, you're just simulating?
We're just simulating the Brownian bridge, and we have 100% acceptance rate.
Okay, so we were using a different.
but it maybe depend on the number of samples you need because you are doing some averaging.
Important sampling scheme, right?
Yeah, this is an
Okay.
important sampling
You're
scheme.
doing
So you
You get no
may-
weights for the
Yeah.
in the important
He's doing
sample.
some kind of.
So anyway, what we found is that we had this situation, so the weight would be 0 or something like that, or when you take relative weight, so they were not meaningful. You don't seem to be having this problem here, but how high dimensional did you try to?
No, we didn't. No, not very high dimensional, but yeah.
So I think so for the Brownian motion we are considering here where there's no drift. This problem I did not experience that problem. But I did when we had Brownian, or we had a stochastic process with drift, and for that we had to modify the scheme to essentially incorporate the momentum in the scheme.
Yes, so that you will talk about that in a different. But that's this, yeah.
And that I will talk about in systems.
Yeah. So, but for this setup, we didn't.
We talked about that in
And that was exactly the low weight in the important sample.
last remark.
Very last one.
When you run that in longer time, you do get point clustering and this simulation. If you were to go to time 10,
You'd get.
you get points that get
Cluster.
I mean, this Brownian motion on landmark manifold is not so great as the stochastic.
This looks pretty good for 10.1.
You have to have the kernels start with point without not too close together for the beginning and
No, the kernel. No, that's why you want to do the estimation of the parameters. No, that's exactly why, because this whole thing is really dependent on the choice of your kernel width and the
if you
scale.
have it as a curve, then you could add points. You would still want to find the same metric, but then numerically it would be terrible.
Yeah, I'm not sure you want to. No, I've come to the conclusion that you don't want your points to be lying on the curve. So this is my last comment, is I want to keep finite number of points that are distributed arbitrarily, not necessarily on your curves and stuff. So that's what I was saying about my thing, is I don't want, and that's why the estimation of the base configuration is linked to the estimation, you know?
So I'm
Sorry.
share station. I need to stop here.
Okay.
Okay. Thank you very much for all the questions. That's good to have questions, but we have another speaker. So thank you.
Thank you.